Hello everyone, this is Ritik Surya and I'm here to present on the topic comparison between Monod's equation and Michaelis-Menton's equation. Before I start with the comparison, I'll give a little bit of introduction and history for both the equations because it's important to know how both of them originated because that's the huge difference between the two. So at the bottom we have this is Michaelis, this is Menton, and this is their equation on enzyme kinetics. The reaction, the equation basically describes enzyme kinetics, and because it's a chemical kinetic equation, it's derived mathematically. Whereas at the top we have Jacques Monod, and this is his equation, which is very similar, but this was derived much later to Michaelis and Menton, and this equation describes bacterial cell growth rate. And uh, one speciality about this equation is again it's derived empirically, so there is no derivation involved, and the entire equation is framed based on mere observations. So I'll start with how these two equations originated, and let me start with Monod's equation initially. So I'll use the same flow in which Monod himself has described the arrival of his equation, on his paper, right? So we all know the bacterial growth curve, right? So we basically start with lag phase. This is where cell growth occurs, and the cells, all of its physiological functions occur, and the cell becomes bigger, right? But there is no cell division, and this is not giving out any yield, and that is why most of the fermentation industries, they're trying to get rid of lag phase as much as possible. Then we have a beautiful, linear log phase, right? So this is exponential or log phase. One great thing about log phase is that is the only phase which is linear and where some sort of a cell division is happening, because again death phase is not linear, right? So this is linear because it's a logarithmic function, and this is where the rate of division is highest. uh, Theoretically it's supposed to go on forever, but obviously the cell starts to decrease, the growth rate starts to decrease until the formation of new cells become equal to the death of old cells, and that is where we enter the stationary phase. There are obviously various reasons why stationary phase has to come. There are limitations like accumulation of toxicity or decrease in substrate, etc. uh, this is not the end of it, because again substrate, if it is remained same, right? If the entire fermentation is in a closed vessel, right? Closed state fermentation, then cells keep giving out toxic byproducts. The competition between the cell almost becomes amensalic, and again without substrate the cells start to die much faster than they are being formed, and eventually the concentration will tend to zero. So that is the death phase. Of all this, we are interested in the log phase again, as I told you, because it's linear. So let us have a more detailed look at this. So obviously, log phase can be put up in this equation: dx by dt is proportional to x. Basically, it says that a small change d in the concentration x. X is the concentration of cell, or I can say biomass of the cell, right? The change in biomass of the cell in a small time t, right? Uh, they say that it's proportional to the concentration of the cell itself. So if I have more number of cells, then basically there is doubling after every generation. So the rate of change of number of cells become much higher if the number of cells itself is higher. So a more clarity to this is given by introducing a constant called specific growth rate, right? So specific growth rate is again it's specific to every single microbial species, and it also changes with respect to various physicochemical conditions like pH, temperature, substrate concentration, and type of metabolism, etc. So to avoid the ambiguity of mu, we bring in something known as mu max. So mu max is the maximum specific growth rate, which is basically the maximum growth, the growth rate particular organism can possess, and that happens in optimal conditions, like optimal pH and temperature, etc. So here are a few examples of organisms with certain mu max values, right? Now what we can do with this equation is we can integrate this. So first let us transpose and bring x to this side and dt to the other side. So we have 1 by x dx, and that is equal to mu dt, right? And I'm integrating this from x naught to xt, some initial concentration to some concentration at time t, where time itself goes from 0 to t. Now, doing that, I'll get, so 1 by x, integral of that is ln x, and because I have x naught and xt, it's basically xt minus ln x naught. And over here again, I have mu as a constant, and uh, mu times 0 is 0, so I'll just have mu t, right? I can again rearrange the terms, so I'll get ln xc is equal to mu t plus ln x naught. Uh, this is the equation basically. Now I can do one more thing. I can basically take an anti-log, anti-natural log of the entire equation. So removing all the logs, I get basically, xt is equal to x naught times e raised to the power mu t. But we are interested in the previous equation, because if you look at this equation, in this form, and compare this to y is equal to mx plus c, clearly it's a straight line. So basically, if I have a plot where on the y-axis I have natural log of concentration across time, and on the x-axis I have time itself, I'm going to get a straight line whose slope is mu, and the intercept on the y-axis is ln x naught, or initial concentration, the natural log of initial concentration. So beautiful. Now we know why it's a straight line, and we know how simple the function is, right? The problem is we were studying about this part, by the way. So the problem is everything that we studied so far is with respect to cells, and cells behave in a very simple fashion. They divide by mitosis and they double in number. But if you talk about a biomass, something a little more complex, say a fungal biomass, right, mycelia, then we have to make a few modifications to accommodate this idea. So Monad also gave a review of literature, but this is something that happened post Monad's equation. A very interesting hypothesis has been made for, in fact, a huge school of thought is put for, how we can correlate to growth rate of, mycelial biomass. Now, one characteristic feature of mycelium is similar to how we say one cell gives rise to two cells. We can say one mycelia branches to two mycelia. I mean, it just a single mycelia branches. So here the multiplication is basically with respect to apices. So if I have one apex here, I'll have two apices here, right? Two ends or two tips, right? So that's a clear correlation. So again, in the next generation, instead of having four bacterial cells, I will have this hyphae with basically four branches, 1, 2, 3, and 4, and so on and so forth. So that is the idea which Ptolemy brought in. He just said that you know the correlation of number of cells dividing of every generation is basically the number of tips, and it's very evident with a lot of experimental evidences, because uh, I mean, if you look at this as well, we can easily say which phase these fungal hyphae might be in. This might be probably in the penultimate stages of log phase. This might be somewhere in the mid log phase, right? And this might be in the early log phase. So we can make such correlations, and branching is very easy to observe as well. But then the question arises, as to when does branching occur? Because we know that cells divide after a certain biomass is reached, after a certain physiological function happens, right? Basically G phase and S phase. After that, we have the mitotic division. Branching also has, there are a few hypotheses that tells us when branching happens. One of the early hypotheses was put forward by Trincy. So This paper states that there is a certain unit length, say x, for instance, right? After that length, only branching initiates. So then after that, I'll have two branches. Then this branch is going to grow until it reaches that length x, after which its branching starts to initiate, right? Which makes perfect sense, because we know that most of these mycelial biomass has a certain standard length after which branching occurs. It's not irregular. But this was not consistent, especially with those mycelium which had uneven, biomass distribution. So we had to bring in, some other. Okay, before that, this is a graph from Trinity's paper. I forgot to put up the slide. Now you can see clearly they are correlating time on the x-axis with length of the hyphae and number of hyphal tips. Basically, number of hyphal tips, it's indicating branches, right? The number of times branching is occurred, and that is easily correlating with the length. But like I told you, this is not consistent with uneven or unequal distribution of biomass. So to solve that problem, we have Robinson and Smith in 1975. They brought up another hypothesis, which is very close to what actually happens. They said that it's not really the length of the biomass, but actually the volume of the, sorry, not the length of the hyphae, but the volume of the hyphae that causes branching to occur. So instead of saying there is some X length, I would say there is certain volume the hyphae has to attain before it can branch. And this also explains as to why certain branches are longer, because they are basically narrower, whereas certain branches are shorter because all of these have the same volume, right? So explains a lot of things. And one more beautiful aspect of Robinson and Smith's hypothesis is, now we know that volume can be directly correlated to biomass. Length could not have been done so because we know there is uneven distribution, but volume and biomass can easily be correlated. And correlating this to biomass brings us one step closer to our initial hypothesis, because if we are correlating that to biomass, we can also bring in the picture of biomass of the cells that was seen in bacterial growth cultures, and that again correlates to concentration of the cells. And now we bring in fact there's another parameter as well I spoke about, that is dn by dt is equal to mu n. So a lot of things which mean exactly the same. In case of bacterial cells, we have the concentration, of the cells. So basically, rate of change of concentration is proportional to concentration. There was another hypothesis that h is the length. So rate of change of length is proportional to initial length. A here is basically volume. So rate of change of volume is proportional to initial volume. And similarly, n could be, so all of this actually, in fact, all of these conclude and boil down to number, right? It could be number of cells, it could be number of apices, number of branching, etc. So number of branching, again, rate of change of number of apexes or number of tips is proportional to initial number of tips, and that is basically correlated using this. We can just go on and we can extend this to also rate of change of biomass as proportional to biomass, as long as the evenness is maintained across the range. We can extrapolate this information. But that's not the end of it, because there was one more paper which was published a few years after Robinson and Smith, that is Pert's paper. And this brings in a beautiful concept which we were ignoring the whole time. All these equations, you integrate all of this, you get straightforward logarithmic curves, right? Integrating this similar to what we did earlier with respect to dx by dt is equal to mu x, right? Integrating that gives us the straight line plot. Now you plot that line, it has no terminal point, so it keeps going on forever. But we know that growth has to stop at one point. So that secession was explained by Pert. Now, Pert explained it with respect to fungal or mycelial biomass, but we can extend that to bacterial growth as well. Now, what he said with respect to mycelium is basically we have freely dispersed hyphae, and they get, like, this is in a medium. So, all of the oxygen content in the medium, the substrate from the medium, everything is accessible to the hyphae. But as the hyphae concentration increases, it reaches a point where it starts to aggregate and clump. Now, uh, one thing I would like to say straight away is this is not universal, and also the way they start aggregating and clumping is very different. The overall, I can say, pellet or aggregation morphology of these hyphae is different, right? And we have studied that. So the morphology can be pointed or globular, star-shaped, thread-like, etc. Now, each morphology has its own saturation point, beyond which it just cannot, allow these substrates to enter into the core of the aggregate or core of the pellet. For example, look at this globular pellet we have. Obviously substrates are accessible to the edges, and these edges keep on dividing, the edges keep on branching, and the growth happens. But the central core, this is where neither the substrate can reach nor the oxygen can reach. And another crisis is there are toxic substances that cannot be eliminated out, because there are byproducts which can be toxic, but they cannot be dispersed out of this core, right, because of the aggregation. Again, depending on species to species, we don't know to what extent this aggregation will be a problem, because again, the morphology and the rate at which aggregation happens, all of this makes a big difference. But now we know that there is a point beyond which the uh, logarithmic phase or the exponential phase just cannot happen. So there has to be a cessation in the growth. And that says now this is another illustration. It's basically speaking about oxygen concentration and how it's decreasing towards the core. uh, there are different radius, and towards the core area you can see the oxygen concentration is almost zero, right? So I mean, very clearly in our equation we were speaking about rate of change of biomass being proportional to initial biomass, right? But this initial biomass, if we consider this entire pellet as having certain biomass x, obviously our rate of change is not depending on the x, because the entire x is not doubling, right? Every generation I can say that only the terminal or the edge, the biomass towards the edges are doubling, right? And these just aren't dividing. In fact, there are cells which are dying in the core. So this is where our curve starts to become more and more flat. From log it starts to become flatter. That is described using this function, which was put in Pert's paper. Now, uh, again, I don't want to go into the mathematics of this function. In fact, there's a huge derivation to this as well. But one thing we need to know is this is basically, he was talking about mycelium. So this is the initial biomass of mycelium, the biomass of mycelium at time t, and k over here is the constant that varies from species to species, and this is the constant that um, plays a role in determining the morphology of the biomass, and hence the saturation point beyond which there can be no exchange of nutrients across the biomass. But even Pert forgot to mention one thing, which was actually mentioned in Monad's paper itself. He forgot to understand that the pellets just don't keep aggregating to larger and larger pellets. At one point there might also be breakage of pellets, and the moment there is breakage, again there is more surface area, and hence the growth immediately spikes up. So in case of mycelium, I just want to make a point that it's very, very complicated. It's not a straightforward, lag, log, and stationary. So after stationary, again, there can be tiny log phases. Again, there can be death phases. So this is like a fingerprint, growth rate that depends from species to species for a given, physicochemical conditions. Now, having said that, we vastly came across two limitations, right? We spoke about the toxin limitation and the substrate limitation. The limitation of the cessation of growth because of accumulation of toxins, and because of limitation in substrate or unavailability of substrate. Now, toxin limitation, to a certain extent, there is a natural remedy to this, right? The organisms can mutate, and they can have different morphology of aggregation, so that toxins have some way of getting released, or the formation of this byproduct can be suppressed to a certain extent, right? So that is not a problem. But substrate limitation, there is no way to escape this, right? Unless and until we are using a continuous growth culture medium, if the substrate is decreasing, there is no way an organism can compensate for that naturally. So our Monod's equation, or rather Jacques Monod, he was more concerned with the substrate limitation. So at the end of the day, Jacques Monod just explained to us what how this substrate limitation can affect the cessation of the growth. He quantified that with his empirical formula. So if you see from region A to B, right? So this is a straight plot, and then we have this equation, and we have seen another form of this equation earlier. Here just that SR is the residual substrate concentration, S is the initial substrate concentration. So subtracting these two gives us the substrate concentration at a given time, and X is the biomass, and Y is the yield factor. This is a constant yield factor, and again this depends on pH, temperature, concentration of substrate, concentration of toxins, and all the physical chemical factors. Very similar to what we studied earlier. This is basically an equation in the same terms. It's just that we are using different symbols. But at this region from B to C, where the transition occurs from log to stationary, right? At this point, basically S becomes equal to 0, right? And beyond that point, we can only explain the growth rate using Monod's equation. So what we see below, right? This is Monod's equation. It explains things very clearly. So we have mu, which is the specific growth rate, mu max, the maximum specific growth rate. These two are substrate concentrations, and this case is another term that Monod introduced. We call it either Monod's constant or substrate utilization constant, and that constant is what explains the entire thing about substrate limitation. So if the substrate utilization constant is higher, then substrate is utilized faster, and hence in a very quick span of time substrate limitation starts to occur, and hence the growth is forced to cease, right? Another thing that can be done, right, with this equation is, let us consider a point where mu is equal to mu max by 2, right? Substituting that, we have here mu max by 2 is equal to mu max multiplied by S divided by Ks minus S. I can cancel out mu max. So I'm continuing the derivation here. So what I'll basically get is Ks is equal to, I have 2S from here, right? Transposing 2 to the top, and then again minus S, right? So Ks is equal to S. That's a wonderful thing, because he just introduced a new constant, and he called that substrate utilization constant. And we need to define a constant when we are introducing it. And this is the definition. So substrate utilization constant is nothing but the concentration of substrate when the specific growth rate is half of the maximum specific growth rate achievable, right? So, a very straightforward explanation or derivation for this, the constant, right? So whatever I explained so far, that is actually the end of Monod's equation, and I have also put screenshots from my Wikipedia page for the same. Moving ahead, coming to Michaelis-Menton's equation, and I will not be explaining this in as much detail, because this is a part of enzyme kinetics, which is not related to bacterial cell division, and this is explained by Ritik. He will be explaining the entire enzyme kinetics. So I will just derive this equation briefly. Now, consider this reaction, and we have different phases over here. In fact, this is a mixture of different equations. So the first equation I have over here is E plus S. E is enzyme, S is substrate, and these are the rate constants for various steps. So I have different possibilities. One is, first of all, enzyme and substrate has to give me enzyme substrate complex, right? Via rate constant K1. Now, few things can happen with enzyme substrate complex. This can either give me, now I have another reaction where enzyme substrate complex can either give me product, right, and detach the product from the enzyme so that enzyme remains unchanged. Now that is a hallmark of enzyme, by the rate constant K2, or there is a third possibility where enzyme substrate complex can decompose, and this is not a good thing, but it can happen as well, and we can't stop it, and that will give us again our reactant and the enzyme, right? So for each of this, let us derive the rate and let us see, how this thing relates to. First of all, we are interested in formation of product, right? This is what we want, right? So let us find the rate of formation of product. So that will be equal to d by dt of concentration of product, which is equal to the rate constant K2 times enzyme substrate complex, right? Again, let me put in the other equations as well. The other rate equation we have, let me call this R1, R2, and R3. Right? So the other rate equations I have is, I have K1 times E and S. So this is basically giving me the rate of formation, or d by dt of enzyme substrate complex, right? Formation of enzyme substrate complex. And I also have the decomposition of enzyme substrate complex, which is by K naught times enzyme substrate, right? K naught times of that. So one thing we know is this enzyme substrate complex is a transient species. This is an intermediate, and hence I can say that rate of formation of enzyme substrate complex is equal to rate of elimination or decomposition of enzyme substrate complex. Equating those two things, I can put in the steady state approximation. The moment I implement steady state approximation, basically the rate of formation of enzyme substrate complex, which is K1 times enzyme and substrate. This is the rate of formation of enzyme substrate complex. That will become equal to rate of decomposition of enzyme substrate complex, right? So that will be K2 times enzyme substrate complex plus K0 times enzyme substrate complex. I can put all the constants towards the right hand side. So I will just have K0 plus K2 by K1, and towards the left hand side I'll have all the concentrations, enzyme plus substrate and enzyme substrate. Now further, this derivation deviates a little from our usual chemical kinetics derivation. Basically all of the constants can be replaced. Now I'll be continuing over here. So all of the constants can be replaced with a constant Kmg, which is our Michaelis-Menton's constant, and then I can have the substrate concentration as just S, again S over there, and I'm bringing a new term which is velocity of the equation V, and that is V max times S by Kmg plus S. Now compare this equation with our monads equation. So our monads equation was let me change the color. So our monads equation was basically mu is equal to mu max times S by Ks plus, right? And comparing these two, we see that the equations are very, very similar, right? The only difference being we have here the specific growth rate, and here we have the enzyme kinetics, the velocity of the enzyme reaction, and also the constants, right? Those are different. We have the substrate utilization constant versus the Michaelis-Menton constant. If we plot Michaelis-Menton's constant, right, that equation on the graph, we get this graph, and compare this graph with our monads equation graph. So another similarity can be drawn very easily. If you just observe this point, right, at this point we have velocity of the reaction, which is equal to half of velocity of the maximum, or half the maximum velocity, or I can basically call this as Vmax by 2, right, at this point. And at the same point I have Km, which is equal to substrate concentration, because Km is basically equal to substrate concentration. and compare this with what happened in our defining our monads constant. So in our monads constant we said that when mu is equal to mu max by 2, our monads constant Ks, or substrate utilization constant, was basically equal to concentration of substrate. Again, very very similar, right? Monads equation over here, and Michaelis-Menton's equation over here, and we see that both of their constants have very similar definition. They are both equal to the concentration of substrates when the maximum, half of the maximum velocity is reached. So again, now I'll basically dwell into the comparison between the two equations itself. And the comparisons are very, very interesting. The first one is, I've been repeating this again and again. They both define totally different things. It's like comparing apple and oranges, right? So Michaelis-Menton's kinetics completely explains enzyme reaction. It's a chemical kinetics based model, whereas our monads equation describes cell growth rate, or bacterial cell growth rate, and that is a completely it's a biological phenomena that is explained. But if you look at the kinetics, they both have very, very similar kinetics. They both have very similar definition to their constants. And even if you look at the plot, again, the sharpness of the monads plot is because of its constant. I told you that this area is logarithmic, and it's a straight line, whereas this area over here is not a straight line function. But otherwise, the overall function of the graph, the overall shape of the graph remains very, very similar, right? And again, we have the same legends in the x and y axis being a little different. So although they are explaining two vastly different phenomena, they are having a lot of similarity with respect to their physical and mathematical significance, basically their kinetics, right? It's very similar, but a huge difference is how we arrive at them. Now when we're talking about Michaelis-Menton's equation, we had a huge not a huge, but rather a simple derivation via which we came across Michaelis-Menton's equation, which is right here in the bottom. Whereas Monad's equation was completely empirical, right? If you even look at our Monad's equation derivation, let me just go back to that slide. You see, in our Monad's equation, we never explained, we never derived anything, right? So both of these, right, all of these were based on observation, right? So even the fact that the curve was logarithmic was purely based on observation. Everything is empirical and experimental. Here, everything is mathematical. Now, another very simple and very interesting relation, in fact, with respect to these two equations is their occurrence, right? There have been various debates about, in fact, various observations that Monad's kinetics happens after Michaelis-Menton's kinetics. And that is because Monad's kinetics explains cell division, but cell division only occurs after substrate has been utilized and some metabolism physiology of the cells happen. And for substrate metabolism and utilization, we need to have enzyme reaction, which is explained by Michaelis-Menton's kinetics. So I can say in a very gross and vast terms, although this is not a definite sequence, but in a very vast bird's eye view, I can say that Michaelis-Menton's kinetics is giving rise to Monad's kinetics, right? Because only when enzymes break down the substrate will get metabolized, the cells will undergo its physiological function, and it will prepare itself to grow and divide, and the cell division is then explained using Monad's kinetics. So that's a very nice sequence that we have, which relates both of them, right? And there was a study in 2000. So there was this paper by Hoover and Egley. So they try to compare these parameters. They called it the monad parameters. Basically, these are the core, key factors which is involved in monad equation. And basically, it is mu and s. Similarly, we have mu max and ks. So they try to correlate between mu and s, that is specific growth rate and substrate concentration, and then maximum specific growth rate with substrate utilization constant. Now, how they did this involves pretty complex mathematics and a lot of experimental data. So they did a metabolomic study, and it's a pretty old paper, so most of the work was manual and not automated. But the end result was, they said that these parameters, right, mu max, s, and ks, they widely depend on the past. I can say the media's past, right, and the the growth medium, the past of the growth medium is basically utilization of substrates. Though, so the conclusion of this paper by Kovar and Elgi is that, this utilization of substrates, the enzyme kinetics, and the metabolomic studies, right, the entire metabolism, all of those are key factors that affect how this ks and mu max, and these monad parameters happen to be, right? So all of this is dependent on the past of the cell. And there's yet another study, and this is much more advanced and it has much more clarity, I would say, because this involves metabolomic construction. It's known, there is this there is this technique called flux balance analysis. So um, Zheng and Yang, let me write the name. Zheng and Yang, they perform this flux balance analysis. So let me explain you what flux balance analysis is first, and then I'll go to Zheng and Yang's result, right? So flux means basically some input getting a processed, some input getting processed to give out some outputs, right? Similar to what we see in our Gauss law in case of electrostatistics, right? So there is some input that gets some sort of a processing and gives out some output. And in our case over here, the flux is basically with respect to metabolomes. So, these are substrates giving rise to products, right? So, basically in a flux balance analysis, the entire process is automated. You just have to provide some inputs, and you have to provide a metabolomic map, right? And then you have to download a few packages, R packages. It's available in Bioconductor, and then you can run it over, and you will basically get a flux based, metabolome. So uh, again, you feed in the metabolic maps, then you give out a few mathematical equations. These mathematical equations list out all the reactions that occur for this substrate to get utilized. And these are all balanced equations, and they all appear to be in this term. So something like, a plus b plus c is equal to 0, where all of these are input, and even the outputs are transposed to the left hand side in as negatives, right? So basically all these equations are solved, and we end up getting a flux. Now what does this flux based analysis look like? This is a simple glycolysis map that I have. It's a glycolysis metabolism map, which was downloaded from keg pathway. And you can see very simple arrows that explains the whole process pretty efficiently. But if I perform a flux based analysis of this, I end up getting this chart. And here there's a huge difference. The thickness of the arrow is varying across different steps, right? So these arrows are thin, these are thick. Now thickness is basically, it's indicating flux. So if I have a thick arrow, then I can say that the flux is very high. So I can say that a lot of ATP is getting hydrolyzed here, but very few ATPs are actually contributing to phosphorylation of glucose, right? Similarly, these, here I can say there's a lot of input and a lot of product formed, whereas here the input is smaller, and these two arrows are merging. So I can bring in a lot of, conclusions based on the thickness of the arrows, which are basically indicating the flux. So Zheng and Yang performed their flux-based analysis. It's a beautiful paper. I think everyone should read it. It's a quite recent paper, 2009, I guess. I put it in my reference section, and I encourage everyone to read it. This is the figure from their paper itself. Again, the actual flux-based analysis and the derivation of the relation is beyond the scope of this presentation. But these are some of the equations that they came up with. Okay, and all of them I have explained. I mean, I've given the description in the right hand side column over there, right? So again, this is a very elaborate explanation which I won't be giving, but the fact is they try to bring in all the factors, all the monad parameters, and all the Michaelis-Menton parameters, and the aim of the study was to derive a mechanism for monad kinetics. So until now, we kept saying monad kinetics is empirical and Michaelis-Menton is mechanistic. But they performed, flux-based analysis, and they derived a mechanism through which the kinetics they obtained was very close to monad empirical kinetics. So they have hence proved that they actually identified the mechanism behind monad's kinetics, and that mechanism is it's brainstorming, because of that mechanism we can understand that monad's constant or substrate utilization constant is actually related to Michaelis-Menton's constant. So they brought in this relation by introducing a factor delta. Again, it has a very elaborate mathematical explanation. There are also a lot of supplementary equations, but the basic I can say the basic thing about delta is it's signifying a cell's metabolic strategy. So it's all about which metabolic pathway the cell chooses, at what constant, at what kinetics it chooses, and what is the mechanism it opts for, because a single metabolic pathway can obviously have lots and lots of mechanisms. So all this is a randomized choice based on very vaguely based on the physicochemical conditions of the cell. But based on this decision, there is certain relation that they have obtained for the substrate utilization constant and monads constant, which is amazing, because they try to basically, we are coming closer and closer towards an approach where we are merging these two equations. In fact, after this paper, I saw some of the very recent papers, some of the papers after 2010, where they are quoting this thing called Michaelis-Menton monad constant, or Michaelis-Menton monad kinetics, which actually has no meaning because they are two different kinetics. But people are trying to merge these two kinetics because they're very, very similar, and keeping them as two different kinetics is just redundant. So we are trying to find some correlation where these two can be brought together as a single sequential kinetics that happens. Okay. Um, Now, finally, I have a few more things, a few more significance of these, kinetics, with which I'll conclude my presentation. Uh, the first and the foremost thing is 1 by Ks. Now, looking at the equation itself, as I told you again, both of these have very similar dimensions because both of them are rate of change. This is rate of change of uh, basically rate of change of the reaction, which is the velocity of the reaction. This is rate of change of concentration, right? Again, they both have a maximum rate of change multiplied by the substrate concentration. They both have again substrate concentration in the denominator, and they have different constants, but these two constants are again related by, I mean, the factor that relates these two is delta, right? Along with that, more similarities for these two equations is, if you look at the significance of 1 by Ks, like I told you, 1 by Ks relates to uh, affinity of substrate, basically cell's affinity towards substrate. Now think about it again, right? Substrate utilization constant, reciprocal of which is nothing but the affinity of a cell towards a certain substrate. But this affinity purely is based on the enzymatic mechanism that metabolizes that substrate, right? So I can say that 1 by Ks is again, taking us very close to the, enzymatic mechanism, and that again merges these two equations together, right? There's another, I mean, there are a lot of explanations about Ks. Some people also say that Ks is it's a function of change in Gibbs free energy, because we know that during cell division and this bioprocess, right, there is obviously change in Gibbs free energy because of all the thermodynamic constants and the substrate, the energy difference in the cells because of substrate metabolism and all that. So the change in Gibbs free energy is described by substrate utilization constant. But Gibbs free energy is all about mechanism, right? Gibbs free energy is a thermodynamic constant that explains mechanism of any reaction to occur. So are we saying that this substrate utilization constant is a function of what mechanism the cell is choosing? Because if that is true, if this is a function of the mechanism in which the cell is metabolizing something, then the substrate utilization constant becomes mechanistic. The moment it becomes mechanistic, the first difference we spoke about, monad being empirical and Michaelis-Menton being mechanistic, that difference is nullified because we are clearly saying that monad's kinetics is mechanistic at the end of the day. So we again have more and more, and there's also a lot of debates on should this be unified or should these be considered as two different kinetics. But I guess all of these debates and arguments settle down with Monad's paper itself, and that is why in the last slide I want to give the most interesting correlation between the two. So this is the original paper by Monad, which was published in 1949, much after Michaelis-Menton's paper. And there are two sentences I want you all to read. One thing is that now here again, symbols may be different from what I used to explain, right? But if you look at this line, right? So he's trying to say that substrate utilization constant or Monad's constant. Now C is here Monad's constant. That is expected to have some relation with respect to enzyme metabolism or enzyme reaction, right? Dissociation constant of the enzyme, which is nothing but our Michaelis-Menton's kinetics. So that is one place where Monad says that his own kinetics is expected to be very similar to and related to Michaelis-Menton's kinetics of enzyme dissociation. And in another place, he says his constant, right, Michaelis-Menton's constant, is much smaller than Monad. I mean, Monad's constant is much smaller than Michaelis-Menton's constant. So if you read this whole paragraph, in fact, I think everyone should read this paper. But two things which you can bluntly conclude is, without any flux-based analysis and without any, mechanistic understanding of the bacterial cell growth, Monad just, very easily he said that his constant Ks is always less than the Michaelis-Menton's constant Kmg. That is one thing. And he said that his constant Ks is a function of Michaelis-Menton's constant Kmg. Although he did not use the terms Michaelis-Menton and substrate utilization constant, he pretty much concluded that in these lines. And with the flux-based analysis, we also know that this function is nothing but delta. So we started with two vastly different equations that were talking about two almost unrelated processes. And at the end of the day, we are still in a conflict as to whether we should merge these two equations. And does this have almost no difference in their significance, right? So these are all the stuff I spoke about. This is a screenshot of my Wikipedia page with the second half of my explanation, and these are the references. Thank you for listening. Thank you.